Hello and welcome to the presentation about our paper TAVeer, an interpretable topic-agnostic authorship verification method. A few words about myself. My name is Oren Halvani and I'm a research assistant at the Fraunhofer SIT in Darmstadt, Germany. My research interest is in digital text forensics. This can be understood as a generic term for a number of disciplines that focus on the question of how to identify information about authors of anonymous documents. One of the most important questions digital text forensics is dealing with for a long time is how to determine whether two documents were written by the same author. Authorship verification, or just AV, is a subfield of digital text forensics that concerns itself with this problem. AV can be used for a wide range of applications, such as continuous authentication, exposing malicious emails, ghostwriting, or in general plagiarism detection, authentication of historical writings, and many, many more. With the increasing number of research activities in the field of AV, a variety of approaches have been proposed so far to solve the AV problem. These are, for example, a number of papers published in the recent years. However, a large number of these and other existing AV approaches are relying on features in the documents that are not always related to the writing style. Many existing AV methods, for example, make use of implicitly defined features, in particular character engrams. Character engrams are overlapping strings, which are obtained by sliding a window of n characters over a document from the left to the right, at least in an English document. But there is an issue with character engrams. Since they're extracted from documents in an uncontrolled way, they capture various text units that, besides writing style, also cover other document properties, such as topic, genre, structure, sentiment, and many more. And this is a problem, because in AV the focus lies on the writing style rather than on other document properties. In the worst case, it therefore can happen that the verification result of an AV method is not really based on a writing style but on other aspects, such as the topic or the genre, which raises the question of whether the method actually serves its real purpose. To counteract this, we have decided with regard to our AV approach to consider only explicitly defined features. More precisely, we focus on 20 categories of topic-agnostic words and phrases, including function words, contractions, several subclasses of verbs and adverbs, and transitional phrases. Note that for convenience, I'll use the abbreviation TA for topic-agnostic. All words and phrases contained in these categories are merged into a single list denoted by LTA, which comprises a total of about 1,000 words and phrases. Based on this list, we now present a number of feature categories that will be used by our AV method. These are punctuation engrams, TA sentence and clause starters, TA sentence endings, TA token engrams, and TA masked token engrams. But before explaining them, it's important to note that for the engram-based feature categories, we consider fixed ranges of values. An explanation why we have chosen the specific values is described in our paper in more detail. Furthermore, it should be highlighted that each setting of n results in a distinct feature category, so that in total we have 11 feature categories where the IDs are shown in the left column. To get an idea what these features now in fact capture, we look at the following example sentence, so that's the way it goes. Punctuation engrams, for example, are obtained by extracting all punctuations from the sentence into a sequence. Then we apply the engram operation, that means the sliding window operation, on the resulting punctuation sequence, so that, for example, for n equals 2, the resulting punctuation bigram is apostrophe full stop. The two feature categories, TA sentence and clause starters, and TA sentence endings, focus on words and phrases that appear at the beginning of the sentence or clause and at the end of the sentence. One restriction here is that they must be contained in LTA, so that here the resulting features are so and goes. The feature category TA token engrams are similar to standard token engrams with the restriction that the underlying text units are either punctuations or single words that appear in the list LTA. The resulting features here are so that's the and it goes full stop. Finally, the feature category TA masked token engrams is also a form of standard engrams with the restriction that one or two topic-related words, note related words here, depending on the setting of n, must appear in the token sequence. Once the topic words are identified, they are masked by the hashtag. The resulting features here are that's the hashtag it, and hashtag it goes. So the hashtag marks a topic-related word here. The takeaway message is that unlike standard n-grams, here we know exactly what specific features are actually captured. Now that we've described the proposed feature categories, we can introduce our AVER approach TAVeer, which is the abbreviation for Topic-Agnostic Authorship Verifier based on equal error rate. TAVeer can essentially be divided into two phases, training and inference. In the training phase, we must provide TAVeer a training corpus which comprises n verification cases labeled as yes and no, where yes denotes the same authorship and n a different authorship case. Once the training has been finished, the resulting model is applied in the inference stage to an unseen verification case. The result of the inference phase is a binary decision, yes or no, as well as a score that describes how confident TAVeer was with respect to its decision. Okay, that was the big picture, and now we take a closer look at the inner workings of the method. First, we have to calculate for each involved feature category, Fi, the distances with regard to all verification cases in the training corpus. The resulting distances are required to determine the thresholds for the respective feature categories. So how we do that? Given Fi, we construct for the unknown and known document within a verification case the corresponding feature vectors x and y, where depending on Fi, a single feature denotes the absolute frequency of a punctuation, word, or phrase in a document. Then, both vectors are normalized by the Manhattan norm so that each vector sums up to 1. Afterwards, we calculate the distance between both vectors using the Manhattan metric. At the end, we get n distances for all m feature categories, which represent the input for the thresholding procedure. Once all distances have been computed, we determine for each feature category Fi its corresponding threshold θ Fi using the equal error rate. Essentially, this is the point on the ROC curve where the false positive rate equals the false negative rate, as can be seen in the illustration on the right. In our setting, all corpora are balanced. That means that the yes and no cases are evenly distributed. We therefore consider the median as an approximation of the equal error rate. The result of this procedure is a set of thresholds for all feature categories where each θ Fi is calculated by the median of the n distances with respect to Fi. In order to construct a model, we further need a similarity function that will help us to estimate the quality of the generated ensembles in the next step. The function must satisfy two requirements: transforming the distances into values between 0 and 1, and calibrating them in such a way that 0.5 represents the decision boundary. For the intended purpose, we designed a simple piecewise function, which is defined below and illustrated on the right. The function takes three arguments: d, the distance; d max, the upper bound of the distance function, so for the Manhattan metric that would be 2, which can be shown easily; and θf, the threshold for the considered feature category f. Note that any other suitable similarity function can be used instead, as long as both requirements are met. In the next step, the ensembles, in other words combinations of feature categories and thresholds, must be constructed. For this, a set fθ is created, which comprises tuples of feature categories and associated thresholds. Given fθ, we compute the power set to generate all possible ensembles. However, here the empty set is discarded, as obviously an empty ensemble wouldn't make much sense. Note that within the power set we distinguish between ensembles and atomic ensembles, where the latter is just a set with only one tuple. Since now we are dealing with ensembles and not with single feature categories, we need an aggregated similarity function, which we denote by sim epsilon, to take ensembles into account. Sim epsilon takes as an input the unknown and known document, d max, so the upper bound of the distance function, and the respective ensemble. And based on these, the function first computes for each feature category and its associated threshold the respective similarity score, given the similarity function introduced in the previous slide. Finally, sim epsilon determines the median for the similarity scores computed for all feature categories, so that at the end we get a single aggregated similarity value. To find the optimal ensemble from all generated ensembles in the power set, we need a ranking mechanism. For this, we define a classification function that will be also used in the inference phase. The function receives the same arguments as sim epsilon and predicts yes, that means same author, if the aggregated similarity value exceeds the decision boundary 0.5. Otherwise, the function predicts no, it means different author. Given this function, we classify all verification cases in the training corpus and calculate the respective accuracy. This procedure is then performed for each possible ensemble in the power set. Now that all aggregated similarity values have been calculated for all ensembles, the question arises which one should be chosen as the final model M. One idea is to select the ensemble with the maximum accuracy. However, in practice, it can happen that there is not only one maximum value. In other words, several optimal ensembles may exist. To find a suitable one, we therefore follow a different approach in which we sort all ensembles in descending order according to the following three criteria. First, we sort all ensembles by their calculated accuracies, then by the number of feature categories each ensemble comprises, and afterwards by the median accuracy with respect to all atomic ensembles contained in each ensemble. Finally, we select the first ensemble from the sorted list and define it as the final model M. Now that we have left the training phase, we can use the constructed model M to classify a new, that means an unseen, verification case. This is done as follows. Using the introduced classification function, TAVeer first computes the aggregated similarity value S new between the unknown and known document. Afterwards, a binary prediction regarding the question authorship of the unknown document is obtained by comparing S new against the decision boundary 0.5. If S new exceeds this value, TAVeer assumes that both documents were written by the same author, otherwise by different authors. Well then, this is essentially the way how TAVeer works. To assess the performance of our approach, we compiled 4 balanced corpora and partitioned them into author-disjunct training and test corpora at a ratio of 40 and 60%. The verification cases within these corpora are characterized by cross, related, and mixed topics. In this context, cross-topic means that with regard to yes cases, the topic of the unknown and known document in each verification case is different, while for the no cases, the topic is the same. It's important to underline that AV methods that perform almost randomly on such corpora tend to be affected by topical bias. In total, we have selected 8 baseline methods, including the current state of the art, which have shown their strengths in a number of published AV papers. After training TAVeer and the respective baseline methods, we applied all approaches to the 4 test corpora, shown on the right table, where accuracy was chosen as a primary performance measure. As can be seen in this table, TAVeer was able to outperform all baseline methods on the 2 corpora C-Stack and C-Amazon, where the first is a cross-topic and the latter a mixed topic corpus. Regarding the remaining 2 corpora, C-Jalp and C-Reddit, which comprise related and mixed topic documents, TAVeer performed closely to the strongest baseline IM, also known as the imposter method. To get a better idea how well the individual feature categories performed on the test corpora, we have inspected the 4 trained models. Using the sim-epsilon function, we calculated for all verification cases the aggregated similarity values with regard to the involved atomic ensembles in each model, and then visualized them as violin plots, as shown below. These plots can be interpreted as follows. The distribution of the similarity values for each feature category Fi are colored green for the yes and red for the no cases respectively. The dashed line represents the decision boundary, so that the better it can separate both distributions and the less they overlap, the more suitable is Fi for the test corpus. When looking at all the test corpora, it can be seen that in particular, punctuation engrams, these are the feature categories F1, 2, and 3, have led to good separation between the yes and no distributions. On the 3 corpora C-Stack, C-Reddit, and C-Amazon, the TA sentence and clause starters, that's the feature category F4, has also led to a good separation, but less well compared to the punctuation engrams. It can also be seen that TA token engrams, that's the feature categories F6, 7, 8, and 9, are only partially suitable, depending on the respective setting of man. However, the TA masked token engrams, that's the feature categories F10 and 11, tend to bigger overlappings in regard to the yes and no distributions, and are therefore less effective. To conclude our work, we would like to highlight the key characteristics of our approach. So the first is generalizability. We have shown that TAVeer can be effectively applied to verification cases with cross, related, and mixed topics, and also that it can handle challenging cases where, for example, the unknown documents consist of only a few sentences. Second is interpretability. In our paper, we have described a simple technique that can be used to interpret the verification results of TAVeer, which allows to gain insight into which specific features contributed to its decision. The third is transparency. All underlying text units considered by TAVeer are predefined, so that nothing else can be captured except these. Fourth is cross-domain ability. In initial experiments, we have shown that TAVeer can be even applied across different domains. For example, we trained the method on Reddit posts and evaluated the trained model on product reviews from Amazon, and also the other way around. And as can be seen below, the results remain reasonably stable. But why is this relevant? Well, in forensic scenarios, training data is not always available. So one option that can be used here is to reuse an existing model in order to verify unseen cases. However, this is an ongoing work and must be further investigated in future work. Besides this, there are also other directions for future work. Currently, TAVeer cannot handle spelling mistakes, which is problematic regarding informal texts. One possibility to counteract this is to consider subword units rather than whole words. Moreover, we plan to experiment with other feature categories that have not yet been considered in our approach, as for example, syntactic categories, abbreviations, and interjections, such as lol or hey, which represent important idiosyncratic stylistic markers. Well then, thank you very much for watching and listening, and let's start the question session.